Hi, this is just a very brief overview of how we get the SHM equations for a pendulum. So let's imagine we've got a pendulum which is of length L, and we've got a bob on the bottom with a mass m, so its weight therefore acting downwards is mg, since weight equals mg. The other force acting, of course, is the tension in the pendulum. Now, if we want to work out which force is actually causing the pendulum to move back towards its rest position, then that is going to be the force acting in this direction. So it's at right angles to the tension. The tension, therefore, doesn't have impact on the restoring force taking the pendulum back to its central position. I'm just going to put in a nice vertical here, and that's because it will help us identify the angles we're going to use. So we've got an angle here of theta. That's going to equal this angle here, theta. Now, if I'm resolving the forces, then if I'm resolving mg in this direction, okay, which is actually against tension, that would be mg cos theta, but resolving mg in the direction of the restoring force along here, that's going to be mg sine theta. So that's the magnitude of the restoring force. And I need to put it in the negative direction because the restoring force is taking it back to where it was going rather than in the direction of pulling it out to its start position. So my restoring force is equal to minus mg sine theta. So what we know is that that is going to equal ma. So I can now cancel the masses, and that tells me that minus g sine theta is going to be equal to the acceleration, which we know from SHM is the same as minus omega squared x, where x is the displacement from the centre. So I've now got minus g sine theta is equal to omega squared x, or minus omega squared x. Now, this is the bit where it gets a little bit complicated, because this expression here, sine theta, we're working in radians, and there is an approximation that says when we're working in radians, sine theta is approximately equal to theta. It seems like a bit of a cheat, but actually this is true for small angles, which is why the SHM equations for pendulums only work at small angles. If we have large angles, that's no longer true. The pendulum no longer really obeys SHM. So that's one of the issues we have to bear in mind. That takes us up to g multiplied by theta, therefore, is going to be equal to omega squared x. So that's the first part of the equations, where we're looking at using the forces to get this far. Now, the next thing that I think is a little bit difficult to get your head around is that we're going to return to the definition of radian to work out what x is equal to. And what we end up with is that x is equal to theta multiplied by L. And that's because we need to think about the arc length and its relationship to theta, and in this case L is the radius. So arc length equals angle times radius gives me arc length equals the angle theta times L, the radius. So if we put that in, we've now got g times theta is equal to omega squared theta multiplied by L. So now we cancel the thetas and we end up with g upon L is equal to omega squared. And now if we go back to our other equations that we know, then we can then use omega squared to work out the time period and the frequency for a pendulum, because we know that the time period is equal to 2 pi divided by omega, and the frequency is the other way round.